Okay, so number 2, we have the square root of 48 a squared b. Now, there's a couple different ways you can do these. If you are real familiar with your perfect square factors, then you can, or you might recognize that 16 goes into 48, I believe. But if you're not that familiar with your perfect squares, then you can also do prime factorizations. And so if you're struggling with cube roots, or if you've seen that 4th root and 5th root kind of thing, and how do you deal with those, a lot of times I just break them down into their prime factorizations. And what I mean by that is give me a factor pair for 48. Just 2 things that multiply to get to 48. It doesn't matter what they are. 2 times 24. Okay. Neither one of those are perfect squares, but that's okay. So we can just keep breaking this down. Let's see here. 4 times 6. And again, you can break it down however you want, because in the end, everybody's going to get the same thing. Let's see here. No matter how you break it down, let's see here. 2 times 2 times 2 times 2 is 16, and 16 times 3. Okay. So this is the same thing. And instead of a squared, I'm going to put a times a and then a b. So what I have here, 48a squared b, is the same thing that I have down here at the bottom, just completely factored out. Now, when you're talking square root, by definition, a square root is a number times itself. So, like the number 49 is a perfect square because we can write it as 7 times 7, and the square root of 49 is 7. So for every 2, since we're doing square root, one of these will come out. So square roots, I ring up 2 at a time. If they wanted cube root, I'd ring up 3 at a time. So for this, if I have 2 2's, and that translates into a 2 coming out here in front. This 2 would be another 2 coming out in front. And then I also have an A coming out in front. What's left over? Well, I still have a 3 and a B. So final answer, 2 times 2 times A is 4a, and then I have times the square root of 3b. And that's my final answer. Now, this is one way to get there. If you recognize right off the bat that, oh, 48, 16, that's a perfect square, goes into 48, you could break it down that way. Some people prefer to do it that method. We could have started off with the square root of 16 times 3, because what is the square root of 16? 4. So the 4 would pop out. We have a squared b. All even exponents are perfect squares because a squared is a times a, so the square root of a squared is a. And then I still have a 3b. So I would still arrive at the same answer, maybe a little bit quicker. But the prime factorization method, I think, will really help you when they're doing cube roots or even 4th roots, and they want you to simplify. You just ring up, if they want cube root, ring up 3 at a time. If they wanted a 4th root, you ring up 4 at a time. So 2 different ways to arrive at the same answer. We have the square root of 5 times the square root of 15, and the directions say multiply and then simplify by factoring if possible. Okay, so 5 and 15, neither one of those are perfect squares, and neither one of those have perfect square factors. So, and if they did, we could simplify first, then multiply, or you can multiply, then simplify, kind of like fractions. You can multiply them together, then reduce, or you can cross-cancel and then multiply. So we're going to multiply. 5 times 15.
75.
Okay. And we get 75. So now I have the square root of 75. Well, we could do 3 times 25. We could just go straight to, that is one that I would probably just go that route. instead of breaking it all the way down, which I could, but you probably recognize that 25 times 3 is also 75, and 25 is a perfect square. So if you do it this way, you just want to make sure that one of your factors is a perfect square, because we can only take square roots of perfect squares. If it's not, and you pick two other factors and neither one of them are perfect squares, just keep breaking it down all the way until they're all prime, and then ring them up two at a time like we did in the previous example. Okay? Yeah?
The only reason why you took the 5 times 15 straight across, say if you substituted that with a 6 and a 17.
You'd still multiply them.
And what if it was already perfect square roots times each other?
If they're already perfect, so if it was like square root of 16 times square root of 9, you could either multiply them together, because guess what? That's going to be a perfect square. Or you can simplify them each individually and then multiply. You'll get the same thing either way. Okay, so this, if you recognize that 25 is a perfect square, well, the square root of 25 is 5, so 5 pops out, and you still have a 3 on the inside. And that's your final answer. If you did not recognize that that's a perfect square and you break it all the way down, you would get 5 times 5 times 3. And ring them up two at a time. And the 5 would come out. Because it's square root. Yes. Because a square root is a number times itself twice. If we wanted a cube root, we'd do 3, because it's a number times itself 3 times. So either way, I get 5 square root 3. Okay, so number 6, we have square root of 14a all over square root 7a. All right, since both of these are under square roots, it means the same thing as if they were all under just the same. And the reason why I'm writing it this way is it's probably easier to see that we really are just dealing with a fraction under a radical sign. And if that radical sign wasn't there and I said simplify, what would you do? 14 over 7 is what? Yeah, so you could do some canceling. That would become 2, and a over a goes away as well. And so we are left with just square root 2. And that's it. Because 14 over 7 is 2. And a over a, those a's cancel. But it's square root of 2 because we nowhere in there could take the square root of anything. So it is square root 2. So it stays under there. Okay, so number 12 says simplify by factoring, and it is the square root of 12. Well, you should already be able to tell me this and how to do this. So if you break it all the way down, you'd get 2 times 2 times 3. Oh, sorry. It's number 9. Let me change that. Sorry. There we go. 9. I was stuck on the number 12. So if we break it all the way down, because we could say 4 times 3, and then we could say 2 times 2 times 3. And then you would ring up the 2 2's, which would give you a 2 on the outside, and then we still have square root of 3 there. Or even at this point right here with the 4 times the 3. 4 is a perfect square, and you can take the square root of 4, which is what? 2, and still have the 3. So you would probably either break it down 4 and 3, or if you would have broke it down 6 and 2, 6 is not a perfect square, neither is 2, so you'd have to keep breaking that down. So you either want to break it down to where it's all primes and you can just ring them up, or break it down to where you have a perfect square factor under the radical. So either way will work. Now we haven't done one that's just variables, which number 11 is just variables. So maybe let's do that one, and then we'll do the adding and multiplying after that. So let's see, we're going to do number 11 next. Number 11 is square root of x to the 8th times y to the 4th. X to the 8th, y to the 4th. Now all even exponents are perfect squares, because what times itself is x to the 8th? You gotta think about your exponent rules. Or if we expanded it and we had 8 x's all in a row, and we're doing square roots, and I ring up 2 at a time, I've got x to the 4th. So this is x to the 4th, y to the 2. All even exponents are perfect squares, and all you have to do is cut the exponent in half. Because x to the 4th times x to the 4th is x to the 8th, and y to the 2nd times y to the 2nd is y to the 4th. No radical sign. That is the square root.
Say the numbers up top were 23 and 17.
Ah, do we have one like that? And if we don't, we'll talk about it. Yeah. What happens if they are odd? Well, we will, no, there is not one like that. So let's talk about that hypothetical.
The test won't have one.
No, it doesn't look like it. So if we had, but your homework, if you haven't done this part in your homework, then you might struggle with that. So let's say it was x to the 13, y to the 3, like that. Let's just make them both odd exponents. So the easiest way is to, well, if they're odd, let's make them even. And how are we going to do that?
X to the 12.
X to the 12 times x. Would you agree that that's the same thing as x to the 13th?
Yep.
Yeah. And then we'll change this to y squared times y. And now I can take the square root of the even ones. The square root of x12 is x to the 6th. The square root of y squared is x6. X to the 6th. And the square root of y squared is y. And I still have a single xy underneath there. So even though they weren't even exponents to begin with, we just did a little manipulate. We kind of factored it. And we made sure one of them was a perfect square. In other words, we made sure it had an even exponent. And then the square root of x12 is x6. Because x to the 6th times x to the 6th is x to the 12th. Because your exponent rules say to add your exponents. So, yeah, we didn't have even exponents to start off with, but we were able to create it.